Okay. Hello, everybody, in person and welcome to another Kent Seminar series. Our speaker today doesn't need much introduction for everybody in the room. I think Punit is famous amongst us, and that's mostly because of his great work here, and also because of a lot of years of experience and work here. Punit was just telling me before the lecture that today is his 8th year and anniversary as a research assistant here in the group. So I think we can congratulate him for that. Also, Punit will be graduating soon and he's going to be moving on to be a research developer and engineer at Graphical. And today he's going to be talking about mostly the topics about his dissertation about engineering bio-asphalt and such. I'll just give the podium to you so you can go ahead and present. I'll help you with the question.
Thank you, Javier. Let me. Thank you, Javier, for this nice introduction, and I thank the ICT family and the organizers of the Kent Seminar Committee for giving me the opportunity to present here today. So I'm a PhD student and I will be graduating soon, and I have got a chance to work on a variety of projects here at ICT. And this is one of the projects which we recently accomplished, and more details on this project can be looked at our website at ict.illinois.edu. Today I'll be presenting a part of this study which we accomplished. Before I start, I would like to thank my colleague Javier, who was pretty much involved in this project, and without whose presence, we wouldn't have been able to accomplish this. I would like to thank the PIs, Dr. Sharma, Dr. Ozer, and Professor Al-Qadi for their constant support and guidance, and Illinois Department of Transportation for being there, and the TRP panel and their members. Illinois Sustainability and Technology Center at UIUC and the Illinois Center for Transportation, research engineers, students, and staff at ICT and ISTC. So I would like to thank them all, and without further ado, we'll start over the topic. So in Illinois, over the past decade, we have seen there has been a significant change in the demand of binder being used in pavement construction, primarily because of the use of recycled materials in asphalt concrete, which has led to an increased use of softer binders like PG 5828. However, the primary binder or commonly used binder available in Illinois is a 6422-22 grade, and therefore, in order to achieve our or accomplish our increased demands of softer grades, use of engineered bio-based additives or variety of additives is kind of promoted and encouraged. This will help us to be more sustainable, and at the same time, we need to make sure that our pavement perform. But the challenges with these proprietary products is their performance, especially the long-term performance, is uncertain. And with that idea, the modified binders using these modifiers were studied in this project. The idea was to look into the rheology, both at small and large strain conditions, looking at the battery of chemical characterization techniques to assess the changes in chemistry happening with these modified binders so that we can relate somehow to its long-term impacts. And again, these all properties were studied at variety of different long-term aging cycles provided in the laboratory environment. Now, the question for us was that whether this long-term really represents long-term, because the whole idea was to ensure that these modifiers or additives kind of perform at long-term. And so we need a benchmark to represent what long-term is. And it has been shown in studies several times that the traditional 20-hour of pressure aging vessel, aging in a pressure aging vessel, doesn't truly represent long-term. And so for us, the question was to answer what really long-term is in Illinois. And that was also accomplished as part of the study. And eventually, these modifiers will be used in an asphalt mix, which is more of a heterogeneous matrix of binders and aggregates. And we need to make sure that whatever we found out from this study of these modified binders, we need to make sure can we translate that to mixture level characterization. So balanced performance of these mix needs to be understood as well. With that motivation, the objective of the study was to evaluate these engineered additives with respect to with their respective modified binders using rheological and chemical characterization techniques, which will ensure their performance over long term. Keeping that in mind, a battery of binder cracking parameters, which has been developed over the years in our industry and in the academic field, we looked at a variety of these parameters and also the chemistry of these modified binders. The idea was also to develop an efficient long-term aging procedure that can allow us to quantitatively assess the impact of these modified binders. And the analysis of these, the long-term impacts would help us eventually establish acceptance thresholds and validate them and fine-tune them as we move forward with these modified binders. So a variety of modifiers were used in this study. Primarily, they were of vegetable oil or modified vegetable oil origin, which is highlighted through green color here. There were a bunch of fatty acid derivatives, some glycosamine based modifiers. One of the modifiers which we were not aware of what it is, but we eventually figured out that it's a vegetable oil. So I will show how it is helpful to look into the chemical characterization of these modifiers as well. And then for the benchmarking, we use Rheology as our benchmark for showing that the Rheology is known to be perform poorly in terms of cracking potential of these binders. So this was considered as a benchmark to see whether these modified binders, where do they stand in terms of their performance when compared to a known performed binder. Also, a petroleum-based additive was also used in the study. So a variety of additives were incorporated. These modifiers were used to modify a standard 64-22 unmodified binder to produce a 58-28, which is the current demand in Illinois. And in order to compare the modified PG5828, we had a reference unmodified 5828, which was also used in the study for comparison purposes to see whether these modified binders could perform equally or where do they stand in terms of a traditional 5828. And there were other bunch of unmodified binders which were used in the study to accomplish different tasks. However, I'll not touch on these binders in detail because of the time restrictions we have. So we'll primarily cover the effect of modification on S1. So the first step was to fingerprint the modifiers, because what we are getting, we needed to make sure that is it something what the manufacturers are promising is really these modifiers. And so FTIR characterization technique was conducted on these modifiers. So the vegetable oils, which are highlighted in green, which typically consist of triglycerides, has a characteristic peak of esters and carbonyl groups present and some methylenes, which is a typical hydrocarbon present in any organic material in oils. And so we could kind of see the fingerprint present in the oil-based modifiers using FTIR. Interestingly, the modifier which in the previous slide I mentioned, the modifier L, which we didn't know, had kind of a characteristic feature like a vegetable oil. So from here, we got some hint that it looks like a vegetable oil. In addition, the modifier H, which was initially known to be a petroleum-based, also had some sort of fingerprint of an oil type of modifier. So that gave us some thought that, okay, H has some sort of oil present. And initially what we know, it was a petroleum base. So this is the first technique we looked at. Moving on, when we look at the other set of modifiers like fatty acid derivatives, we can clearly see again that the typical fatty acid derivative will have a hydroxyl group and the carbonide presents, and which is what we can see in here. And it's different from the vegetable oils. So again, kind of helps us to fingerprint what actually is being present in these modifiers. And it can be a good tool to kind of do a QA QC for these modifiers if they are proposed to be used in future. Furthermore, we had other set of modifiers like Rheology, okay, which didn't have any kind of oil presence, more of a hydrocarbon like an asphalt binder, and also modifier G, which was exceptionally high in some sort of acyl group, C single bond O, which is because of the structure of typical glycolamines, which again satisfies the structure and what was given initially as a modifier. So based on the FTIR characterization, we were able to at least validate what was given to us was a valid modifier and it belongs to the right category. Moving on further, when we looked at the molecular size distribution within vegetable oils, even though they have similar carbonyl and ester peaks, we saw that in terms of their molecular weight, they are different within itself. So we found out that 3 categories based on the inventory we had. So some had bimodal distribution in terms of molecular weight, some had single peak, and one had a flat peak. Within the fatty acid derivatives also, we saw that there were 3 peaks, and again, these were different within each other. So both the fatty acid derivatives were not similar. They showed that they had differences in their molecular weights. The modifier K and H had a wider distribution, which is more like an asphalt type behavior. And again, from here, we saw that modifier H, which was initially proposed to be a petroleum base, kind of shows that it is like, based on the molecular weights, it's like petroleum, but it had oil-like characteristics when we look from FTIR technique. Glycolamine had the least molecular weight and was again kind of oil-like behavior, single peak, single species of molecular size present in these glycolamines. So it had the least molecular weight. So together, if we put these 2 techniques, we were able to at least identify what was present in H. So this can be a very useful tool moving forward if these modifiers, these additives are being used in the binders, and if you want to kind of keep a quality check on these modifiers. Other additional techniques of chemical characterization techniques were conducted on these modifiers to see their elemental composition. And interestingly, like some of the modifiers like G had a significantly higher nitrogen and oxygen, and which can be explained by their typical structure they have. Also, H was slightly higher in sulfur compared to others, which again supports the idea that it might have some asphalt components because asphalt has some sort of sulfur to start with. So these were some additional characterization which we did, and probably when we move forward in the presentation, we'll see how they can connect to answer some of the questions or the questions we had. We did the SARA composition. Most of the oil-based modifiers were resin-based, and the Rheology was kind of drastically different in terms of SARA composition. It had a very high quantity of insoluble residue and high saturates in it, and we'll see how this type of composition can affect the performance. Also, modifier G, interestingly, was soluble in water. So that is something to keep in mind as we were moving forward. We encountered these behavior of these modifiers. We also looked at thermal stability of these modifiers, and modifier G was very low on thermal stability. It was the lowest, in fact, the lowest among all the modifiers. These are some of the bullets I would say we'll touch again when we move at the end. So main takeaways from the modifier characterization was that we were able to verify what most of the modifiers were, and were also able to report modifiers like H, which had a composition of oil and petroleum base. Modifier G was low on thermal stability. That has to be taken care of because we deal with the material which is exposed to high temperatures at the time of placement and construction. So that's something we need to take care of as we move forward. Rheology had a significantly high residue, which is like, we can assume it like a rock-like behavior. It's not soluble in typical typical asphalt solubility. It doesn't have typical solubility like asphalt. The residue, which may have issues with compatibility. And most of the vegetable oils were kind of similar in nature. However, the molecular sizes shows that within the bunch of vegetable oil-based modifiers, there are differences. And that can affect performance as we move forward. So fingerprinting proves to be a useful tool for QC and can be used to keep control of formulation changes as we are using these bio-based derived products. And these bio-based or bio-derived products usually change with the source. And so it's important if you're using it in pavement construction, the QC should be maintained well so that we can keep the control of the quality of the product being incorporated in these pavements. So these modifiers were then incorporated into a base binder to produce a modified version of 5828, and the binder were evaluated for rheology and chemistry. So moving with the rheology, the first step was to modify all these binders to a same level of SuperPave PG. So all these modifiers were used to produce a PG 5828, and within this green box of PG 5828, they were produced in a way that they are very close to each other. So the idea was to produce equi-stiffness binders, and based on SuperPave, these equi-stiffness binders will tend to perform technically, they will serve the same purpose. However, we'll see how it's not the case, as we know that these modifiers are different, have differences in chemistry, and that can impact the performance of the binder depending on the aging condition they are exposed to. And so these modifiers were modified in a way using a base binder to produce 5828. Just a note that we were not able to modify a Rheology using this base binder. However, it was close to 5828, so we kept it in our inventory of characterization. It's very close to it, but it was not able to modify Rheology with this base binder. If we change the base binder, we were able to move this into acceptable 5828, which I will not be able to discuss the effect of source, but can be looked at our report. So in order to assess rheology, we looked at small strain parameters coming from binder testing using a set of BVR tests and DSR tests, and also looked at large strain parameters. For the sake of time, I'll go over some of the parameters, what they reveal about these modified binders. So we saw that all those modified binders were kind of equi-stiffness binders and were within very close proximity of in terms of SuperPave PGs. So the first test, which first parameter we looked at was delta TC. Delta TC is a parameter which gives us an idea about the relaxation potential of a binder under creep loading at low temperatures. And so a lower delta TC would suggest that the binder is more prone to cracking. We got the delta TC at different aging conditions as highlighted before, single PAV, double PAV, like 40 hours of PAV and 60 hours of PAV. And what we saw that now these modified binders, which were equi-stiffness, are separated. So it was clearly observed within the single PAV aging cycle that Rheology had a very high delta TC compared to other modified binders. Also, the base binder which we used, most of the modifiers were able to show an improvement in delta TC compared to the base binder use, so which is a good thing in terms of single PAV. However, except that of Rheology. As we moved to 2 PAV, 3 PAV, we saw the differences were more apparent, especially when you look at like fatty acid derivatives, the yellow ones and the blue one like glycolamine. So the chemistry started to play a role in kind of separating these as you further age in terms of delta TC. So glycolamines and fatty acid derivatives showed some better relaxation potential as we move further. And differences were more apparent after PAV cycles. So with the addition of these modifiers, we were able to improve the delta TC parameter from a base binder, which is kind of good. However, Rheology was not able to, and which kind of supports what we are seeing in the in other literatures too. Another parameter, global rho parameter, which is a stiffness dependent parameter and has an empirical relationship to binder ductility, was also evaluated. Higher global rho parameters suggest that the binder is more prone to cracking. Now, since we saw similar kind of effect as we saw in delta TC, the more we were able to see more apparent differences starting 2 PAV. So at this point, I'm just showing the 2 PAV results, but the trends were similar and were more clear as we move forward with 2 PAV. So again, we see it's a stiffness dependent parameter. So S1 here is a 6422 binder, which is a little stiffer binder, so we cannot compare with other modified binders. So this is something we need to keep in mind when we are looking at global rho parameter, that it's a stiffness dependent parameter. So we need to have binders with similar stiffness if we are planning to compare. So again, Rheog is significantly higher on global rho, which suggests that it's more prone to cracking. As we see, most of the vegetable oils kind of fall within the same range along with the petroleum base. And again, glycolamines and fatty acid derivatives shows a better global rho in terms of susceptibility to cracking. So lower, the better. So again, with two different tests, we were able to see that how these modifiers may have an impact, and even at high aging cycles. So again, they have better resistance based on these numbers, like glycolamines and fatty acid derivatives. Moving on, some of the other small strain parameters which can be related to cracking were, one of them is viscous to elastic transition temperature, and typically higher viscous to elastic transition temperature or crossover temperature suggests that the binders are more prone to cracking. And this parameter is more of a stiffness independent. And so here is just a representation of what it means. So if at the viscoelastic transition temperature or crossover temperature, if you are under this temperature, if you subject your binder to temperatures below this temperature, your binder behaves more in a brittle way, elastic way. And if you are at higher temperature, it behaves more in a viscous way. Again, looking at the 2 PAV results, we see that there is now, since it's an equi-stiffness, we can compare S1 to other modified binders, and you can see how there's an improvement with using most of these modifiers except Rheog. And again, glycolamines and fatty acid derivatives kind of show a better viscous to elastic transition temperature, which suggests that these binders have a better susceptibility, better resistance to crack. So when all these different parameters put together, we saw that they have a very good correlation. These small strain parameters have a very good correlation amongst each other. However, some specific parameters like viscoelastic transition temperature or crossover temperature is mostly correlated to most of them. So some of them are from different test type, like a low temperature test. Some of them are at different points in the master curve of the binders, and these parameters kind of indicates that for small strains, these parameters can be replaced from one over the other, and VETT helps to predict other parameters in a better way. Now, binders are not always exposed to small strains. In reality, they are much more. And so a new parameter using linear amplitude sweep test was developed as part of this study, addressing some of the limitations of the LAS test interpretation, which is as per AASHTO T391 or -20, which was recently updated. The parameter was developed, delta G peak, delta G star peak tau, and Javier, it was part of the Javier's thesis where he proposed this parameter. The parameter is basically represents change in the modulus or the shear modulus of the binder where at the peak shear stress. So the capacity of a binder to until it reaches the peak shear stress and how much does it lose suggests what delta G star peak is. And so higher the delta G star peak tau, the greater damage tolerance the binder would have. So if I can sustain more loss of delta G star until the peak shear, I think it's a better binder as it can, without failing, it can sustain those strains. So the effect of aging, with aging, what we anticipate with this parameter is that the aging will make the binder more brittle, and so the damage tolerance of that binder will reduce. And so if we take one of the examples, this is what we see with aging. We see that there's a decrease in delta G star peak time. So this parameter was used to kind of evaluate the large strain behavior. If you look at all these modified binders, which I showed before for small strains, we clearly see here that modifier K had the worst impact on the modified binder. However, the trends which we were seeing before, like glycolamines or fatty acid derivatives, they are okay. One of these fatty acid derivatives are different from each other. Other vegetable oils kind of comparable performance to other modified binders. So the correlation of this large strain parameter was not well correlated with the other small strain parameters, and which can be expected because these are two different tests subjecting the binder to different strain levels, and so it's not expected they have a similar behavior. However, binders like K, which is extremely stiff binders, will still be able to pick in both the tests. So delta G star is a more direct measure of damage tolerance, as I showed, that it measures these stresses and strains to higher strain levels, which usually in small strains we don't see it, but in reality it can be. So it is a parameter which should be looked at in addition to the small strain parameters, as it is giving us some other information. So main takeaways from the rheological part was that beyond a single PAV, the differences of the modified binders were more apparent, as I showed, and then followed by that, we just showed two PAV results. And small strain parameters were correlated to each other, and so can be used as surrogates. So one unique parameter like crossover temperature can be used as a surrogate to represent the small strain behavior. And also the Rheology was consistently showing the worst performance, both at large strain and small strain. Glycolamines and fatty acid derivatives had superior performance throughout. However, I didn't mention here, but we also saw that glycolamines had a higher mass loss, which kind of connects to low thermal stability of the modifier itself. Large strain behavior, again, it's a little different from what we saw from the small strains, but it again picks up the Rheology, which is extremely stiff binder, and so it was shown to be working to pick up the Rheology. But again, the ranking in terms of other modified binders, it was not pretty correlating to the small strain, which we don't expect. So now looking into the modified binder chemistry, how these modifiers change the chemistry, and when we kind of assess these modifiers at different aging levels, how does this chemistry change? So one of the ways to look at it is through FTIR spectra, and the typical fingerprint region of the binders is somewhere here between 1800 to 800 wave number. And if we zoom in and see, there are multiple functional groups like carbonyl groups, which are often associated with cracking potential, and sulfoxides too. So if you have a higher carbonyl sulfoxides, the binder tends to age. It shows that binder is more oxidized, which suggests that it has been aged. There are other functional groups which doesn't usually change with aging, like aliphatic or aromatics, carbon double bond carbon single bond hydrogen, things like that. So two parameters were assessed. One was carbonyls. Now I'll go a slide back. So carbonyls are usually depicted here in these two peaks. However, when we picked up the carbonyl index, we only are picking just the one peak. Now I'll answer this when we go later, because we don't have an answer at this point. But when we looked at the field investigation, we realized that only one specific peak works as an indicator for aging. And another parameter was combining both carbonyls and sulfoxides. So these are kind of indices which we use to assess the chemical changes. The impact of aging on these oxidation indices from FTIR for the vegetable oils was pretty consistent within each other. Both the indices, one the carbonyl base and the sulfoxide index, they were close to each other. However, there was a kind of increase and then there was kind of a plateau or a decrease for the sulfoxide. It is because it may be attributed because the amount of sulfur present in the binders is generally low. So once it's exhausted, you don't see much change in sulfoxide. But the carbonyls, you do see more changes because it's more quantity. When we looked at other modifiers, the rate of change, again, with aging, it was observed that these binders are aging and these indices are predicting it. But when we looked at modifier G, which was supposed to perform better, again, it's much more flat curve compared to other modifiers, suggesting that aging susceptibility of this modifier is less, which may be a reason why the rheological performance with time, with aging, was not that detrimental compared to other modifiers. For the rheob, again, the rate was similar to that of other modifiers. And if you look at sulfoxide, again, it was pretty similar. The two things which we learned out of these indices was, again, this is the unmodified counterparts. So again, pretty similar behavior. Sulfoxide kind of plateau after 2 PAV because of the lack of sufficient sulfoxides or sulfur, whereas carbonyl is still going. So both of them kind of complements what happens with aging. However, with the carbonyl index, what we saw that for one of the modifiers, we couldn't capture the effect. So we need to see what went wrong there. However, if you go by two things, one, the index value, typically the higher carbonyl suggests there's more oxidation. However, when we put these all modifiers together, it kind of doesn't make sense, just the value. So we also have to look at the rate of aging. That's where we saw that how G was really less susceptible to aging. When we looked at modifier K, it was hard to predict in terms of rate because the rate of K was similar to others, which kind of doesn't make sense when we look at the rheology because the aging of K was significantly higher. So we'll see what probably did the change here. The rest of the modifiers appear to have similar impact in terms of rate and index values. Same with the carbonyl and sulfoxide group. However, there was a decrease after 2 PAV. So maybe we need to consider that after 2 PAV, we see that there is a either it becomes flat or it decreases because there's not enough sulfoxide if we are planning to use this as a qualitative measure to evaluate aging. Again, the index value for G was low and the rate was also low. Rate was similar in terms of sulfoxide, but in terms of carbonyl, the rate was low. So again, we were not kind of conclusive in terms of chemical characterization. However, if we look at individual modifier, we see that with aging, the rate increases, which makes sense. But when we put them together, we still have to identify why there are differences. When we look at the modifier weight distribution, modifier binders weight distribution, typically with aging, your large molecular size on this side is large, on this side represents small molecular size. So it increases, which makes sense because you're oxidizing the binder. And so the component of large molecular size will increase. With modification, you see that in modifier G, we see an improvement. We also saw it in rheology. And we also saw it in the FTIR. The rate was low usually when we looked at the carbonyl index. So in order to kind of qualitatively evaluate these, we divided these two areas into two parts, one for large, one for small, and then got some parameters like molecular weight distribution peak and area-based parameters. And when we look at them, what we see is that the rate of change with respect to aging for these modifiers is pretty consistent. For the rate is pretty similar for these vegetable oil-based modifiers. However, the absolute value differs. And now the higher the value, we anticipate that it will be more prone to aging, but the starting point is high. It can be because of the chemistry they have, but these were the differences, but the rate was consistent. But we didn't see much of the differences in terms of rheology. So that's where we cannot answer at this point whether the absolute value, how does it work? But the rate was consistent. Moving on to other set of modifiers. Again, when we looked at rheob, it was pretty close to other modifiers. It was hard to distinguish. Modifier G and modifier B had relatively flatter slopes compared to other modifiers. If we look at both of these area or peak based parameters. So both of these parameters are doing the same thing. If you look at one, we see that modifier B and G has much lesser susceptibility to aging compared to others. These are unmodified binders, again, similar rate levels, but again, index values are slightly different. And we still need to investigate that even though the index value to start with is a little higher, their performance in rheology are pretty similar if you look at the vegetable oils or set of other modifiers. So these indices kind of capture the effect of aging. With aging, they increase, which makes sense. Rate of aging was low for fatty acid derivative, which was B, and G. Again, this is kind of supporting the rheological results which we found. And other modifiers appear to have similar impact on the rate at this point based on these two testings, what we saw. And it was difficult to distinguish based on just the index values, because previously higher carbonyl, higher aging. However, it has to be kept in mind that rate also plays a role. So that absolute higher value can be because of a certain chemistry in the binder, which is not taking part in the rheological, not taking part in creating a brittle binder or a binder with much more stiffness. So the main takeaway from the chemistry testing, what we saw was the oxidation and weight-based indices kind of tracks binder aging, but it's hard to say when we put them together. The rate of change is an important parameter, which we never used to look at. We mostly used to look at the index values. So we have to consider the rate of the indices in addition to the absolute index values. Now, we didn't see any significant change in chemistry or drastically different chemistry as we saw in rheology for rheols. And this can be attributed to the insoluble residue. Typically, the insoluble residue, if you remember what I presented before, that when we ran the SARA composition, there was a high insoluble residue in rheols. Now, that insoluble residue can be any inorganic material, which cannot be picked up in these tests. And so that imparts some sort of compatibility issues within the binder, and that may attribute to the poor rheological performance, which we couldn't see in the testing we performed like FTIR or GPC. But we did saw in SARA composition of the modifier itself. So wrapping up, this is how we saw that how chemistry complemented in some of the modifiers complemented the rheological results, and some of the modifier testing helped us to see why some of the modifiers were not working, even though we didn't see that in chemistry, but we saw it in rheology. Now, the next question was to assess these binders for long-term aging. We really need to know what long-term aging was. And throughout the presentation, I was presenting that 2-PAV was kind of distinguishing at this point, but we'll see whether that 2-PAV really represents long-term, or it's even more or less. So for that, a bunch of field cores were collected across Illinois at different aging conditions. We collected cores varying from 5 years of life to 31 years, and the one which is 31 years was right outside from our parking lot, the oldest one. And so we have a variety of aging conditions subjected to field cores were collected, and we're kind of trying to correlate what exactly it represents in terms of PAV. So this is the list of field cores which were collected, and they were collected from different parts of the Illinois, northern part, central part. We got one from southern part, but not many. However, most of them were concentrated around the northern region. So you can see 31 years right outside ICT. Most of these binders represented 6422, which represents Illinois climate. So care should be taken when I present the results. Some parameters are stiffness dependent. So we need to make sure that when we read those results, they represent 6422, because it will be different for 5828. And some parameters are not stiffness dependent. So we'll try to see where we need to be careful about the stiffness dependent parameters. So like Glovero parameter, it is a stiffness dependent parameter. And what we see that along the depth of the pavement, there was clear extent of aging. At surface, significant aging, all the way from somewhere between 2-PAV to 3-PAV. And when we put all those field cores from the surface in terms of the aging level aging duration, we see that these are the most of our binders which are from between around 10 years of life. That was used as a benchmark for long term. So most of the field codes were collected in this range. And if you see that there is some sort of trend which shows that this parameter is kind of helping us to see that with aging, your GRP parameter increases. And what we saw that at surface, this is where our interest is for long term. And this box can change based on what your long term is. So here, for the sake of for considering long term, we are considering a range of 8 to 12 years as a range, typical range of long term aging. And what we see is that most of these binders which were placed in the field, somewhere if we go by the standard 600 kPa criteria, which is the maximum GRP one should have, doesn't fit in well. So probably this is where we fit for Illinois kind of binders, somewhere around 2 PAV, which kind of shows from our result that starting 2 PAV, we see more differences. So probably 2 PAV is what is at least the criteria should be if you're looking at certain parameters. Moving on, and this criteria of 600 kPa, again, it's a stiffness dependent parameter. So again, depending on what aging condition or what aging condition or what binder PG you are considering, we should be considering thresholds based on that. So this has to be looked at. If you look at another parameter, which was viscoelastic transition temperature, it is a stiffness independent parameter, and we see that along the depth, we clearly see there is a trend and we see the gradient. And if we plot all of them together, we see a nice distribution with aging duration. And most of these binders, which are area of interest is 8 to 12 years, kind of represent long term, is close to PAV. So definitely PAV aging is not the way to go when we are looking at the long term performance of these binders. This was the parameter which was recently developed as part of this study, delta G star peak. And we saw that with aging, this parameter decreases. Here, we saw an interesting curve, and which makes sense which makes sense that with unaged condition, the binder is too soft that this parameter doesn't have enough damage tolerance. With aging to RTFO, it becomes a little stronger, so it has increased stiffness, which kind of helps in resisting the damage. But as we move further, we see with increased aging up to 3 PAV, it decreases. Along the depth, we saw similar kind of behavior, that at surface it's significantly lower delta G star, which suggests it is very brittle. But at the bottom, where the binder is probably not aged too much, you see again lower values. But as you move up the surface, you see a nice trend. Now these are the same, all binders are the same in the same section. This belongs to the same section. But when we put this together with different binders, we don't see a clear trend. And this reason could be because these binders were placed at different times and they have different composition. Few of them are polymer modified binders. So we cannot see clear distinction with aging, but we do see that with the depth, we see this trend, which makes more sense. And so if we want to look at aging duration, we need to make sure that what binders we are looking for. So we need to have information about the chemistry of these binders, the base binder, the moment base binders changes, things changes. So that will definitely have more impact when you're looking at these binders at large strengths. So again, no consistent trend, which kind of makes sense because these are tested at a much larger strains. And so chemistry also plays a role. Some are polymer modified. So polymer modified binders behave differently, especially when you subject it to larger strains. When we looked at the chemistry, remember I mentioned that we omitted one of the carbonyls. We see that with aging, only specific carbonyl increases, not all carbonyls increases. So this is something corresponding to oil kind of behavior, which we don't anticipate to increase with aging. So it should be taken care of that what carbonyl functionality you are considering when you are considering aging. Similarly here, there's not much increase because it didn't have that oil kind of properties, but you do see an increase in carbonyl specifically to this wave number region. So again, you should be careful with what carbonyl index you should go for if you want to assess. If you look at the distribution along the depth of the pavement, at surface you see more more of higher index values. Makes more sense. And if you look at the distribution, there is kind of some rough distribution because these are more populated points. If we have more populated points at 17 years or 20 years of age, we might see a distribution. That distribution within an aging level makes sense because of differences in chemistry. If we look at the other parameter, similar behavior we see. However, for the sulfoxides, we do see that the aging extent represented by these numbers is somewhere between 2 to 3 PAV, which is more close to what we saw with the other rheological parameters. So main takeaways, which one of the parameters which I didn't mention was here because of the time constraint, that the impact of aging, field aging on binder stiffness and phase angle was different. The way it aged the binders, and if you look the binders from stiffness perspective, the aging was more significant. From the phase angle perspective, it was not as significant when we compare it to PAV aging levels. So it shows that the aging in the field is a little different from what we are doing in the lab. And so that may affect some of these parameters because they are a combination of both phase angle and stiffness. And so in the lab, we need to make sure if we are aging these binders, we should have this into account that field aging is slightly different and it can impact stiffnesses and phase angles in a different way. So what we saw that 2 PAV or greater may be more suitable for Illinois type of climate. If we say around 10 years is a long term, if you go 15 years, things might change and we can change accordingly. Small strain parameters tells us that they're kind of interchangeable and we can use specific parameters, but you need to be careful when establishing acceptance criteria if you're using stiffness based or stiffness independent parameters. Similar trends for 2 PAV, 3 PAV, aging can be as significant as 3 PAV, but 2 PAV kind of works at this point as it saves time and also helps us to distinguish this modified binders. And we also saw from rheological perspective that starting 2 PAV and more, we probably see more difference. And also chemically, we saw that only specific functional groups kind of affect aging. Not all carbonyls are the same. And therefore 2 PAV was used as a practical way. So now we have an aging protocol 2 PAV, which we were using to kind of differentiate these binders. I think we're running short of time. So we also did some quick mixture performance testing to see whether these modified binders work well or not. So I will just present the result for lab mixes, which were made from the specific modified binders. And what we see is here that the performance, what we were seeing in rheology, that modifier G, which is a glycolamine, and modifier C, which is a fatty acid derivative, was performing the best throughout. However, when we went to the mixture characterization, we saw that G was no longer the best performing. Others make sense. K was the worst, second worst or next to worst, which makes sense from the rheological perspective and the chemical from the rheological testing. But the G was something which we didn't anticipate, which may be attributed to low thermal stability, which we mentioned. So when we go back to the modifier itself, we saw that modifiers were low on thermal stability, modifier G, and that might have impacted when we were producing the mixes at high temperatures. Whereas C was not much affected. In the balance performance, again, K and C were kind of not performing over long term. However, the other modifiers were performing okay as per the IDOT specifications. So I will not go over the plant mixes because of the time. So I'll just kind of summarize here that with rheology, we saw that glycolamines were performing better. However, they were low on thermal stability. Fatty acid derivatives were good. Rheop was always the worst. When we looked at the chemistry, we couldn't see clearly. However, we clearly saw that glycolamines were low on aging susceptibility, which makes sense and which can support the rheological findings too. And when we looked at the mixture performance, glycolamine was opposite. Fatty acid derivatives were in the right direction. Rheop was performing worse, was in the worst direction. However, glycolamine was not. So throughout the rheological testing, we saw it's good, but then it was not. And probably the reasons could be its low thermal stability. So we need to further assess that. Modifier G in general was high in nitrogen. Modifier C, which was fatty acid derivative, was high in nitrogen. Typically, nitrogen-based compounds are good in resisting oxidations. They're good oxidation inhibitors. So might add to the behavior of these modified binders. Rheob was high in saturates and insoluble residue, which kind of supports why we were not seeing anything in chemistry. Chemical test what we performed, but we definitely saw in rheology and mixture performance. So with that, I would like to conclude the presentation and I will open the floor for the questions. Thank you.
For the sake of time, I think we're going to take one only question. We're going to wrap it up. Here's Punit's email. You can email him other questions, or you can stick around at the end. I do see one question. We're going to take this match.
Yeah, okay, I'll ask the most simple one and ask you the rest later. So thanks, Punit, really nice presentation. This was good to see and it's a lot of work. Regarding, you showed the mass loss.
Yes.
And is this the mass loss just for the rejuvenator, or sorry, the modifier, or is this for the binder modified with modifier?
So I showed you two mass loss in the presentation. One was through TGA, which was just for the modifier. We also did the mass loss. Typically, we do it with RTFO aging, and that was around 3% with the modifier.
So you're having mass loss of 3% of that binder modified with modifier.
Yes.
But how much is the modifier content?
It was 6%. So technically, I'm losing half of the modifier.
Exactly. I mean, you're not losing more than 0.1 or 0.2% with the binder. So
Yes.
You're losing almost half the modifier.
Yes.
So then is any test on the modifier relevant if you're losing anyway half the modifier? I mean, is it necessary to test that modifier, or we should just say this modifier cannot be used?
So based on the study, what we found out that probably that mass loss definitely affects when we do the mixture characterization. But when we were looking at that, and that's why we were interested in that, we wanted to go with that and see. And we saw that even with the binder rheology testing, if we're losing so much, how is it improving the rheological performance? And one of the answers, what I think could be, is that that's a glycolamine. Amines are typically, they resist oxidation too much, and so they are good in resisting aging. And so probably what we are losing is definitely impacting in terms of weight in mixture, and we can see the difference. But when we look at rheology, it still has some benefit, and it's not letting, based on the other parameters we look, both large strain and small strain, we didn't saw that it's affecting the binder performance significantly, because there is still some amines present in that. So what we can think of is, what if we kind of re-engineer the modifier in a way that it's more thermally stable? It may help us retaining that performance. So we are looking into why mixture performance was affected. We want to find out what were the reasons, so that we can go back and is it possible to fix the mass loss, and it can help us with a better modifier. So except mass loss, the modifier G was throughout performing the best, like exceptionally well.
So then, just as a quick follow-up, if you want available amines, I mean, there's WMA and those kind of additives that are very high in those that are already available.
Yes.
So why should we use the modifier where we're having a high mass loss if those are already on the market and well established in our field?
So this is something.
Anti-strip also, right? Yeah.
Yeah. So this is something which was available to us, and that's a very good question. Why should we use that? And we should definitely not use a binder with modified binder with such type of modifier. So the learning from here is either we fix it or we cannot use it. That's the whole idea. But that was interesting to see how it was improving the properties in rheology. So if you're just looking at rheology, it will always come out to be the best.
Yeah.
But if you go to mixtures, that's where the whole game is. That's not performing. And so we need to be careful about these type of modifiers.
Exactly. Thanks.
Thank you. Thank you, Punit.